After having discussed the different types of batteries and different battery characteristics in the previous videos, it is now time to discuss charge controllers in this final video of this section. As I said in the battery videos, the charge controller is principally concerned with the battery-connected systems and thus is part of this video series. Here, I will explain to you about the different functions that a charge controller can perform in a PV system. This is followed by getting to know a couple of PV system topologies which use charge controllers in them. So, let's get started. The charge controller performs an important part of the PV system. Particularly, they are important in standalone PV systems where battery storage is a necessity. In such a PV system, the charge controller is generally connected to PV modules. It is also connected to the battery and other loads of the system. So why do we need this component? To answer that, let's consider a simple PV system where the PV module is connected directly to the battery and no charge controller is present. When the sun intensity is constantly changing throughout the day, the current produced from the PV module will also vary. Because of this current fluctuation, the charging rate of the battery fluctuates and may, under some illumination conditions, exceed the rated current to the battery, which would be harmful to the battery. To prevent this situation from happening, the device that is inserted in the PV system is the charge controller. Suppose in the same scenario, when the sun intensity is very high, the battery will get charged very fast due to the PV module producing higher currents. When this battery reaches its full capacity, the PV module will still continue to produce current feeding into the battery. At this point, the battery will begin to get charged beyond its capacity. This is called overcharging of the battery. Overcharging the battery has a negative effect on its performance. It leads to several problems like gas formation, capacity loss, or overheating, thereby reducing the lifetime of the battery. But with the help of a charge controller, this problem is avoided altogether. Here the charge controller plays a vital role in decoupling the PV array from the battery, thus stopping the battery from being charged any further. Similarly, on the other side of the PV system, when the battery is supplying energy to the load, during periods of low sun intensities, there will be a possibility that the battery might be fully discharged. Discharging a battery beyond a specified lower limit, or over-discharging the battery, also has a detrimental effect on the cycle lifetime. Thus, here too, the charge controller plays a vital role by preventing the battery from being over-discharged. This is achieved by disconnecting the battery from the load. At this point, the system will not be able to power the load, but this is vital in preserving the battery's lifetime. Another function of the charge controller is current regulation. Consider a battery which is being charged or discharged at a faster rate than a nominal rate. This leads to a reduction in the efficiency of the battery. But a charge controller with a proper current regulation can be used to control this by maintaining the rates close to its C rate, which is the battery's nominal parameter. The charge controller does this by imposing limits on maximal currents flowing into or out of the battery. Additionally, a charge controller also has a back charge regulator integrated into its circuit. This function is very useful, especially in a PV system that does not have blocking diodes in its PV module or its PV strings. With the absence of blocking diodes, there is a possibility for batteries to charge the PV modules when operating at low voltages. This means that the battery will impose a forward bias on the PV modules and make them consume the battery power, which leads to the solar cells heating up. A charge controller will prevent this situation from happening. In addition to current regulating functions of a charge controller, it can also function as a voltage regulator. Some charge controllers that are currently available in the market have MPP trackers included in them. With the presence of the MPP tracker, the charge controller can also act as a voltage decoupling device where the PV voltage and the battery voltages are decoupled. This allows for the PV modules to operate close to its maximum power point voltage and the battery close to its rated voltage range. Now that you know that a charge controller is meant to protect a battery in various ways, let's take a look at a few ways that this can be accomplished. You just saw that one of the main functions of the charge controller is to prevent overcharging of the batteries. There are two ways this can be achieved inside the charge controller. The first method is called the series charge controller. In a series charge controller, overcharging is prevented by disconnecting the PV array until a particular voltage drop is detected, at which point the array is connected to the battery again and charging can continue. On the other hand, in a parallel or shunt controller, overcharging is prevented by short-circuiting the PV array. This means that the PV modules will work in short-circuit mode, and that no current will flow into the battery. Both of these topologies also ensure over-discharge protection. This is achieved by power switches for the load connections, which are appropriately controlled by the charge controller algorithms. Finally, I will talk briefly about a couple of PV system topologies where a charge controller is used. As we know already, the charge controller is an important component of an off-grid PV system. So when deciding on the type of charge controller to be used, a proper decision has to be made for the right type of PV system. For example, when a PV system with only small DC loads are involved, the charge controller can be the component that brings all the other system components together. They are the PV modules, the batteries, and the loads. Such a PV system is more common in very remote areas where the loads are comprised of just a few DC lamps and fans. The advantage from this is that a 12 volts is enough to power those loads. Hence, it is relatively safe to operate because of such low voltages. Also, by using a simple PV system, the cost involved is also very small. On the other hand, when using a slightly larger PV system that also powers big AC loads, the inverter is also connected to the charge controller in addition to the battery setup. Now, loads are connected to the inverter in such a configuration. The system voltages may be 12, 24, or even 48 volts. Now you may notice that the battery is connected directly to the inverter here, not through the charge controller. This is because charge controllers may not be able to handle the high currents delivered by the battery to the inverter. This means that the battery discharge protection that is generally available in a charge controller is now available in the inverter. This is sometimes accomplished by an automatic shutoff below a certain threshold voltage, since the voltage drops with the state of charge of the battery. Thus, in this particular scenario, the charge controller prevent only overcharging of the battery, while the battery discharge protection is carried out by the inverter. So, to recap, in this video, we studied about the different functions that a charge controller can have in a PV system. We came to know that in the standalone PV system, a charge controller is an important component that protects its PV modules and batteries from getting damaged and prolonging their lifetimes. They are also useful in getting an optimum power from the PV modules when MPP tracking is integrated inside them. With this, we have come to the end of the section of videos on batteries. I hope you enjoyed learning about cables and batteries in PV systems.